Hello everyone, welcome to my channel PK's tutorial, and today in this video lecture I am going to discuss velocity of transverse wave of a stressed string. Please like, share and subscribe my channel, and don't forget to press the bell icon so that you can get latest updates of my videos. So let's begin. Let us consider coordinate axis x-axis and y-axis, and let this red line be representing the stressed string. The blue curves represents the vibration of the stressed string up and down along the y-axis. Let A be any point on the vibrating string at a particular instant t with its coordinate axis x and y, and B be another point with its coordinates x plus del y, y plus del y. The tension force at the point A and B will be same here. And the direction of the tension force at the point A can be given by drawing a tangent at the point A, and let this be tangent AT. Here T represents the tension force at the point A. Similarly, at the point B, we can get the direction of the tension force by drawing a tangent, and let this be BT. Now this tangent AT makes an angle θ1 with respect to the x-axis. So the component of the tension force at the point A can be drawn as such. That is, this is the horizontal component of the tension force, and this is the vertical component of the tension force at the point A. Since this angle and this angle are same, so this will be T cos θ1 and this will be T sin θ1. Similarly, at the point B, let BT make an angle θ2 with respect to the x-axis, and let this be the horizontal component at the point B, and let this be the vertical component. So this will be T cos θ2 and this will be T sin θ2. So this is all about the diagram. Now let us write the statement, let AT and BT be the two tangents at A and B making an angle θ1 and θ2 respectively with the x-axis, and also let tension force at A and B be capital T. Now since the displacement of the vibrating string is taking place only along the y-axis and there is no displacement along the x-axis, it means that the horizontal component of the tension force are nullifying each other, and we are only left with the vertical components. So the resultant force on this element AB is given by only this vertical components, and it can be written as such. That is, the resultant force F on acting on this element AB is T sin θ2 minus T sin θ1. Now if our vibration is very small, that is θ1 and θ2 are very small, then we can write sin θ1 is equivalent to tan θ1 and sin θ2 is equivalent to tan θ2. Substituting this in this, we'll be getting F is equals to T tan θ2 minus T tan θ1, and if we take T common, we'll be getting this. Now we know from the definition of the tangent that tangent is nothing but tan theta, which is equals to dy by dx for this xy plane. So in place of tan θ2 we can write this, and in place of tan θ1 we can write this, that is ddx y plus del y minus ddx of y. Thereafter, in place of del y we can write this, because from the definition of the partial derivative we know that del y is equals to this. So in place of del y I have written this, and further mathematical approach gives us this, and here this and this get cancels out and we are only left with this, and let this be the equation number 1. Again, if we assume that small m represents the mass per unit length of the stressed string, then we can write mass of the element AB, which we have chosen, whose length is what? Del x is equals to mass per unit length into the length of the element del x. From the figure you can see this is the element del x of the stressed string. So from the definition of the resultant force we can write the resultant force on the element dx is equals to mass of the element, that is del m, into double differentiation of the displacement of the string along the y-axis with respect to the time, which can be further written as this, that is, in place of this del m I have written m del x from here. So let this be the equation number 2. From equation 1 and 2 we can write this is equals to this, and further mathematical approach will lead us to this, and further we can rearrange this and we can write it in this form. So let this be the equation number 3. Now if we compare this equation 3 with the general wave equation, what is the general wave equation? This is the general wave equation. As you can see here, the format is same as that of the equation number 3. Only the difference is what? Here we have v square and here we have t by m. It means what? If we compare equation 3 with this general wave equation, we get that v square is equals to t by m, and thus we get the velocity of the transverse wave. Hence, comparing equation 3 with the general wave equation, we can write the velocity of the transverse wave of the string is v is equals to root over capital T by small m, that is tension force by mass per unit length. So this is our final expression for the velocity of the transverse wave of a stressed string. And that's all. Thank you.